Right. So what I want to tell you about is some of the physics and also maybe a little bit of something that's relevant to doing the perturbation theory in the many-body localized phase. Okay, so many-body resonances in the many-body localized phase. And I'll tell you what I mean by this. Okay, and so let me present it one way. Okay, so the model I introduced last time, which I called the standard model. Let me just write it a little bit differently here. So remember, it's a spin-a-half chain, closed system, right? And we're looking at we're going to in particular look at the eigenstates, because we're interested in whether the eigenstates are localized or whether they're thermal. And I'm just going to write the Hamiltonian a little differently just for the purposes of doing perturbation theory, or talking about perturbation theory more accurately. So SIZ plus J SIZ SI plus 1Z I plus 1Z. So and then plus J SI perp dot SI plus 1 perp. Okay, so I've separated off the Z component of the coupling and the off-diagonal component of the coupling, right? And so now this part, we can just get the eigenstates of this are just spins aligned along the Z-axis, either up or down. And then this we treat perturbatively, okay? So in some sense, this is simple. We can treat this in the basis where this is diagonal, and then this causes hoppings between eigenstates of this, because this basically flips spins. Right? This goes from one spin up, the other one spin down, and flips them. Right? That's what this term does. It's a flip-flop term. Okay. Right. Now, and remember, these fields are random. These are static random. And in some sense, the issue is, what's the status of this perturbation theory? And this is related, say, to KM theory, right? That when you do a perturbation theory like this, you have to worry about, are there resonances, right? Does the perturbation theory work, or are there resonances which prevent it? And that's what I'm going to begin addressing. Yeah. Right bigger. Okay. 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 So right. So I want to talk about these resonances here, and let me show this in a picture. Okay. So now this is. It's a one-dimensional system, so I just draw a line here. That's the one-dimensional system. And let's take a particular region of this system of length L, so L sites. And what I want to ask about is resonances within this region. And so what that means is I want to consider all states that are identical in this region, and identical in this region, but I can flip the spins in here. Okay? So here we fix the state. Just write it in here. So in here, we have L spins, and so we have 2 to the L states possible inside of here. Okay? I'm going to fix a pattern, a random pattern of spins up and down along here, random pattern of spins up and down along here, but then consider all possibilities inside this interval here, right? Okay. Now, and let's talk about it first before we do the perturbation theory. So just set this equal to 0. So we're going to have 2 to the L states, and their energies are the sums of these random terms, right? So you're going to have well, let me put it this way. You're going to have a density of states, which goes as 2 to the L, up to factors of, you know, I'm focusing on the exponential factors, right? So the range over which the range of energy over which all these states are distributed is just of order L, right? Because, you know, the highest state will be the ones with all these terms as positive as possible, and the lowest energy states will be the ones with the spins such that all these terms are as negative as possible, but the biggest that range can be is of order L, right? But there's 2 to the L states in there because I've got L spins and I can put them all up or down. I'm talking about many-body states. So we have a density of states which goes as 2 to the L. And so what that means is we have amongst these states, right? So let me just call these a set of states. We have a many-body energy level spacing, which goes as 2 to the minus L, right? At least as far as its exponential dependence on L. Okay, so that's a many-body level spacing. Right? So I have this energy range inside of which I have 2 to the L states, which are randomly placed. So they're here, you know, this is just Poisson distributed energies to first approximation, right? I'm assuming they're just completely random. So that's the many-body level spacing. This is the typical between, right, if I just pick up one of these states and ask what's the nearest state in energy, it'll be an energy difference that far away. And then the typical smallest gap, right? So I've got these randomly placed points. The energy differences are of that size typically, but I have 2 to the L such pairs, and so the smallest one will actually go as 4 to the minus L, right? So if we just take an interval, we put down 2 to the L points randomly, the average spacing is 2 to the minus L, but the spacings are distributed all the way down to 0, and the smallest spacing will be of order 4 to the minus L, okay? So that's just sort of the statistics of 2 to the L states with random energies, right? Which is basically what we have here. And now we want to couple them perturbatively and ask what happens, right? And we have to worry about small energy denominators. You know, when you do perturbation theory, you got to worry about these energy denominators. And I'm just talking about standard quantum perturbation theory, okay? And that's what the resonances are, okay? Now, right. So if I worry about one of these resonances, let me just right. So here's energy, right? And here's one level, and here's another level that's nearby, right? And these differ by typically of order 2 to the minus L in energy. And if you ask, how do these two states differ? I've got L spins. They're, I've considered all states with them randomly up or down. and two states that just happen to be nearby in energy. They just happen to be nearby in energy because these random numbers hi on the spins that got flipped, they just added up to near zero, right? And you have 2 to the L chances, and well, actually, what I want to say is the 2 nearby states, but what I mean is nearby in energy, typically differ by L over 2 flips. Just, I have L spins. I'm just basically picking up 2 random states which happen to be nearby in energy, so they're going to differ by of order L over the 2 flips. L over 2 spin flips. Half the spins will be the same, half the spins will be different, because they're just 2-state spins. Okay? So now if I ask, when I do the perturbation theory, if I want to ask what's the effective matrix element for a hopping from this state to this state, I'm not going to get that at first order in perturbation theory, right? Because first order in perturbation theory is just going to flip 2 spins, right? I've got to flip of order L spins. So it's only going to show up at order Lth order in perturbation theory, right? So these are connected only at of order Lth order in the coupling here, which flips the spins, right? And so the effective matrix element, when you do perturbation theory, perturbation is small, something that's Lth order in perturbation theory, it's going to go as, actually, it's not strictly Lth order in perturbation theory, but let me just say, let me write it this way: J to some constant times L, right? It's not necessarily going to be exactly Lth order. It might be L over third order or something like this, right? And J is small, so we can just write this as e to the minus some other constant times L. So the picture, what I have in mind, what I'm trying to do here is talk about resonances at high order, because we want to ask, is this perturbation theory going to converge at high order? How do the tails fall off? So that's why I'm focusing on resonances involving many spins. Yeah. Yeah.
Naively, why should you worry about resonances if the effective matrix elements are exponentially small with the system size?
Because the gaps are exponentially small with the system size, right? Right. So that's the thing. Yeah. Normally, when you do perturbation theory, if the high order terms, you don't worry about them if they're exponentially small. But in this case, by going to high order in perturbation theory, you can access exponentially many different other states, right? Because when I go to Lth order in perturbation theory, I can access things which flip of order L spins, and that allows me to access 2 to the L states, and therefore find one that's degenerate within 2 to the minus L, right? Right. Exactly. But let me, right, what I was going to say, what I'm doing is kind of naive, so really, to talk about this properly, you sort of maybe need to think a little bit renormalization group-like or whatever. The idea here is, okay, so before I do the perturbation, I've got all these energy levels, right? Let's say I carry the perturbation theory out to L minus first order, and all the energy levels shift little bits, right? And they're rearranged. And then now I'm doing the Lth order, and I've made these additional matrix elements. And so these level spacings I'm talking about, they're not the levels I'm coupling at Lth order in perturbation theory, they're not the energy levels from 0th order, the energy levels that have already been shifted by the lower order perturbation theories, and now I'm just putting it in at this level, right here. Okay. So when I consider two such levels, which are almost degenerate, and put in the Lth order perturbation theory contribution, what I have is a little 2 by, for those two states, it's just a little 2 by 2 matrix. And so let me say delta is the levels, let me just call this level spacing delta, right? And the 2 by 2 matrix looks like this, plus delta over 2, minus delta over 2. And remember, delta is perhaps 2 to the minus L, or in the worst case, 4 to the minus L, or even smaller. And then we have this off-diagonal matrix element, which is going exponentially in L as well, right? And so we just need to look at this matrix to do the Lth order perturbation theory, right? And it's a small perturbation if the off-diagonal term is small compared to the diagonal term, right? That's the situation when it's a small perturbation. But we have a resonance when e to the minus, the off-diagonal term is greater than or of order the level spacing, right? So that's just, and when this happens, what does it mean? It means at that order in perturbation theory, once I've done the perturbation theory, I have to do degenerate perturbation theory, and I get a very strong mixing between these two levels, right? And so now my eigenstates have a lot of entanglement on this scale, right? Because on this scale, the eigenstates are actually linear combinations of two completely different spin patterns, right? And that's the beginning of destroying the localization. So that's why this is of interest, is because, right, if you have a lot of those resonances, that's what thermalization is, right? Thermalization is just the proliferation of resonances, and now your eigenstates are just linear combinations of all configurations. Whereas right now, what I'm asking is, when do my eigenstates become linear combinations of two rather different spin configurations? Okay. And therefore produces entanglement over some scale, right? Not just short-range entanglement, but longer-range entanglement. Okay. So when this is true, so let's just call these two spin patterns N1 and N2, right? So these are two spin patterns which are, like I say, exactly the same over here, exactly the same over here, but in this interval, they correspond to different spin patterns. Is a resonance, meaning the level spacing is small compared to the coupling. So if the level spacing is negligible compared to the coupling, we know what the eigenstates are. They look like 1 over root 2 N1 plus or minus N2, right? So this is a sort of a caricature of a strong resonance, right? You just make a linear, even and odd linear combinations of the two patterns. The real situation is, you'll have something that's, 60% this and 40% that, or, something like that. Okay.
And what is the timescale from this localized peak to this resonance peak?
Well, it's not really a time scale. So the time scale I'm talking about right now is, it's quantum mechanics, so the timescales are set by the energy gaps. So right now, if I'm looking at resonances at this order, what I'm looking at is the physics that will give dynamics on timescales of order 2 to the L, right? But right now, let's just say we're doing eigenstates. So we're just trying to diagonalize a Hamiltonian. And so there's, I'm only talking about timescales because I'm talking about energy scales. Right? I'm just trying to find the eigenstates of a quantum Hamiltonian. Okay, so here you can see why, at least superficially, why in one dimension the many-body localized states can be stable, and why it's actually a non-trivial thing for it to be stable, right? Why they can be stable and why they can actually not be stable, right? Because what we've got this term from the perturbation, which is exponentially small in L, right? And obviously, if I turn this j down very small, I can make this exponential decay faster than either of these two. But if I let the j be big, this exponential won't decay faster than this one, right? And so I can go into the regime where you always have resonances, and I can go into the regime where the resonances are rare, and those are the two different phases, right? Okay? So stability of the Mbl phase is roughly where, so for stability of the many-body localized phase, what you want is you take a candidate state and you want to ask, is that state localized, right? And if that state is localized, if that state at every place you look, at every length scale you look, you can find a resonance, then that state's probably not localized because it's resonant with states everywhere, right? And every spin in here is gonna be able to flip. So, yeah?
Dimensionality enters because the argument for the energy spread changes because of the perimeter.
Yeah, right. If we were in 2 dimensions and I did a patch, well, okay, this is not clear, right? Because, of course, in 2 dimensions, if I took a patch of area A, the level spacing would be exponentially small in A. But if I wanted to flip all the spins in that area, the term in perturbation theory would also be at 8th order. So this argument here does not treat one dimension, it doesn't discriminate between one dimension and higher dimensions.
But the 2 to the area states will be spread out over a larger energy window because many of them will have perimeter contributions that raise.
No, because we're paying attention to the exponential factors, right? What you're talking about is power law factors, which at large L are negligible, right? So the issue about MBL maybe not being stable above one dimension really doesn't show up in this discussion right here. But one dimension, I'm more comfortable in one dimension, and one of the big motivations for trying to think about all this is thinking about developing the DMRG method to get these eigenstates, exploiting the fact that they're in the many-body localized phase, the entanglement is small, and so we really want to understand one dimension because one dimension is where we can, we actually have hope of really making some progress on this, right? But let's stay in one dimension, okay? So naively, stability of the many-body localized phase seems to require that the typical matrix element goes down exponentially faster than the typical level spacing, right? So that would be e to the minus c twiddle L less than 2 to the minus L, right? And so that's just a small enough j, right? Because we know this is, we can make this decay faster than this just by taking j small enough, right? Okay. And so that's one comment, okay? This seems to allow MBL with get this right. Yeah. 2 to the minus L, but greater than 4 to the minus L. Right? So if we're in this interval, what does it mean? What does it mean? It means if I take a typical eigenstate and look at a typical location in that eigenstate at length L, I will do this comparison, and I will see, oh, the chance of there being a resonance there is exponentially small in L, right? Because I'm assuming this exponential is stronger than this exponential, and so the chance of there being a resonance is exponentially small in this regime. But then if I go in here, I take not a typical state, but just a typical Hamiltonian, and I look in this region of length L, and I look at all the eigenstates in that interval, I will find a resonance, right? Because there will be many pairs of states. You know, the smallest gap is 4 to the minus L, and so there'll be many gaps that are smaller than this, right? Because this is bigger than this, right? And so in this interval, I take a typical Hamiltonian, look at a typical location, and there are resonances on scale L, and there's resonances on all scales. And now if you go back to what I was talking about yesterday of building these localized conserved operators out of all those states. Remember I said you needed all the states to be localized, and out of those states you build the operators. And now it basically means those operators contain processes involving resonances on all scales, right? And so you can see how potentially, and this we don't really know. What I'm telling you is about what we're trying to sort out, but I'm just trying to give you a sense of the issues. That it's possible that in this regime here, that the many-body localized phase might be stable, but actually, in any efficient way, formulating these local conserved quantities might not be feasible because they have to contain the information about resonances out to infinite scales, because those are there basically in every sample at every location, right? So that's sort of an interesting point, that even though yeah.
What happens if e to the minus cl is smaller than 4 to the minus?
Well, okay, so that's the regime where a typical sample at a typical location should not have resonances at all scales, and that's the regime where doing the perturbation theory and getting the conserved operators should be the easiest, right? So this is presumably no MBL. This is MBL, but maybe quite difficult to do the perturbation theory, actually carry it out and get the information. And then the last regime is the sort of deepest in the many-body localized phase, where it should be the easiest. Now, there's also some, let me just go over here. Okay, so I've got, if we have a resonance, right, so I think I've made an argument that these resonances, they are present always, because these gaps, they have a typical value, but they could be distributed down to arbitrarily small. And when you have a resonance, the eigenstates look like this, right? So if you take a large many-body localized system, look over large distances, and look at a given eigenstate, you will find some places where it looks like this, where over that interval there is a resonance, and the eigenstate is a linear combination of two different spin patterns there, right? And why, I guess I should go over here. So now let's get to the, say something about the dynamics. So these resonances, they're of interest for a number of reasons, right? They're obviously the difficulty of treating the phase. It's the proliferation of the resonances that presumably causes the phase transition out of the many-body localized phase into the thermal phase, where in the thermal phase, the eigenstates are linear combinations of essentially all configurations, and so that's just a super big resonance.
So, in terms of standard diagnostics to detect a many-body localized phase, would there be any difference between this phase that you're talking about, where perturbation theory may not be very efficient, and indeed in the Mbl phase, where you would expect perturbation theory to be efficient? I'm assuming that would correspond to e to the minus c tilde L less than 4 to the minus F. That would be your...
Yet. But okay, so the way, right, okay, so let's go to dynamics. So when you have a resonance, you have two closely spaced eigenstates, which differ by these spin flips, right? And so what that means is you have a matrix element of a local operator. Yeah, let me put it this way. Right, so we have these two states, N1 and N2. And let's say in N1, let's say, spin 0 is up in N1, and spin 0, some particular spin is up in this configuration and down in this configuration. There's a whole bunch of other spins that also flip between the two configurations. Let's look at a particular one, right? Okay. And so when you have a resonance, that operator, SZ0, operating, say, on psi plus, right? So what does that give? It gives up plus a positive coefficient when it operates on this, and a negative coefficient when it operates on this. And so therefore, this is proportional to psi minus. And the matrix element is of order 1, right? So it gives a matrix element of order 1 between these two eigenstates. And so what it means is this particular spin will have a dynamics, a relaxation time, or a time scale in its dynamics, which is set by the inverse of this splitting, which is of order e to the minus c times L. So this actually dominates the low frequency dynamics in the Mbl phase. If you take any local operator of the kind of thing you could observe, and we noticed this because we were thinking about the low frequency conductivity, or low frequency polarizability in the many-body localized phase, and you ask what dominates the low frequency behavior, what gives the, you find that it's dominated by these large-scale resonances. So if you're at very low frequencies, to get a matrix element of order 1 and therefore dominate the signal, the way you do it is you have a resonance like this. Resonances on smaller, Okay, so when should I stop? 2 more minutes. Okay. Okay, so this is, let me just say a couple more things. I'm just trying to give you a flavor of the issues we're working on these days. So these are, these are resonances involving just 2 spin configurations. Right, those are definitely there. But then there's another issue, which I mentioned last time. So now remember my phase diagram here. So here's the Mbl phase. Here's the thermal phase. And, okay, so in the context I'm talking about here, let's say we're over, this is the randomness. So we're at this point in the phase diagram where we're in the many-body localized phase, but the thermal phase is nearby. Okay? And so now, again, I draw a picture of real space, and I can have a region of some length which is locally less disordered. Right? So just by chance, in this particular region in real space, my random fields were smaller than they were on average. So this region wants to be thermal. Right? If the disorder stayed small through the whole sample, the whole thing would be thermal. But really, this just is just by chance, the random fields were small. Right? So you have this little thermal region inside an MBL region. On the macroscopic scale, the system is localized. So this is a Griffiths. This is what we call a Griffiths region after Bob Griffiths' paper, where he talked about effects in statistical mechanics of random systems due to rare regions. And a Griffiths region is basically a little region of the sample which is trying to be in the other phase, on the other side of the phase transition, but it's just of finite size, so it can't really do it, right? Now, this is a different type of resonance. So in the context of the many-body localized phase, this is a different type of resonance where there are 2 to the L states inside this region, and they're all strongly hybridized with each other because the system is actually trying to be thermal in this region, right? And so these are resonances with many configurations. And these will occur also with a probability which is exponentially small in the length. And so the picture is, when you're deep in the many-body localized phase and you look at the low-frequency dynamics, it's dominated by these resonances involving just 2 configurations, and you can get those any place. You just pick up special states. So these are due to just special states, not a special region of the disorder in the Hamiltonian, right? Whereas So that's what dominates the low frequency dynamics deep enough in the many-body localized phase. But if you go closer to the transition, the more likely way of getting a resonance isn't due to these special states, but due to a rare region of the Hamiltonian, namely a Griffiths region. And that's what dominates the low frequency dynamics as you approach the phase transition. And if you want to read a little bit more about this, we have a recent paper. This is Krishnan et al. In, well, it's certainly on the archive, 2015, and it's in PRB now, 2015. If you want to read more discussion of these kinds of issues. Okay, thank you.
So I just wanted to understand this last part of the discussion. So there is a small region where there is this thermal phase.
Right.
Right. So let's say I have in that phase diagram that you wrote. So I start from that highly random point, so somewhere there, and I just tune that parameter slowly down here.
Right.
So then when I come close to that phase transition point, then if I look at some particular region, there is a good chance that I'll find a thermal phase in that small region.
The chance of this happening goes up as you approach
exactly.
the phase, of course.
Yeah. So if I closely watch the energy level spacing in that region, so is there some level crossing? Or
well, there will be, the level statistics will start approaching GOE level statistics, right? So if I just consider, okay, so to do that carefully, what you would have to do is you'd have to pick eigenstates which were the same over here and the same over here, but were different only in this region, just like I was talking about before, and then look at the energy level statistics of just those eigenstates. And in this region, it's trying to be thermal, so the level statistics, instead of looking Poisson, would start moving more towards the GOE level statistics.
Okay, so but so it doesn't necessarily have to be level crossing.
Well, in a random system like this, you never have level crossing, right? So there always is, for any process, a non-zero off-diagonal matrix element. So there's never actual level crossing. Everything is a Landau-Zener crossing. It's just a question of how fine in energy you have to look before you see that the levels don't cross, but it's an avoided crossing.
Yeah, avoided.
Right.
Yeah, exactly. Yeah. Thank you.
Yeah.
Since you talked about ETH, so I guess ETH kind of means that if I look at the energy as like expectation of some observable as a function of energy, it's kind of smooth, right? If ETH is satisfied.
Yeah, the expectation value of an observable in the eigenstates as a function of energy would be smooth, right? Whereas in the Mbl phase, it would be jumping up and down from one eigenstate to the next because each eigenstate is different.
Okay, and what about the cross, the off-diagonal elements? That's also that's still exponentially small. I guess that's still true, is it?
In ETH. Yes, but once you're in the Mbl phase, like I told you here, you have these pairs of eigenstates where off-diagonal matrix elements can be of order 1. Even though the two eigenstates actually differ by a large number of spins, right? That's what's a little bit counterintuitive here. I could have two eigenstates which differ by many spins, but a single spin operator can have an off-diagonal matrix element of order 1, right? And so something involving many, many spins can actually dominate the single spin local dynamics. right? Which is not obvious that would happen, but
Just make some